Okay, what I'd like to do for this next session on survival analysis is, first of all, to go over some basic definitions that we need to have. There's an entire vocabulary for doing survival analysis. And then start getting to the meat of the matter, which is how do we estimate how various predictors affect the hazard, the rate of dying, okay? So we've seen that modeling age as our outcome is an attractive idea, but the way we fit the model, the assumption that we make about what the distribution of age at death is, can have a big influence on the results we get. They're too sensitive to that assumption. And that has led people to try to model survival in different ways. And we've also seen that if we take the ratio of how many people die in a time interval to how many were still available to die in that time interval, that's a rate. And we don't have to make any assumption about what the distribution of the age at deaths are in order to do that. So that's an attractive alternative, and that's why people have started to fit hazard models. Now, we also went through and saw that we could fit survival curves, which is what fraction of the population is still alive at any time, again, without making an assumption about what that distribution ought to look like, because we can do it non-parametrically. We can use these Kaplan-Meier curves, and we could stratify our data. We could take men and women and fit separate curves, and instead of Kaplan-Meier curves, we could smooth those curves if we wanted to, and we could see that the survival curve for men and women are different. However, in general, epidemiology is now a field where we have a lot of predictors. And we just can't break the data down more and more and more and more and more. And that's why we do regression analysis. That's why we do it for blood pressure. That's why we do it for binary variables. Yes, no. Did you have an asthma attack yesterday? And that's why we need to do regression analysis for survival data to estimate how that rate varies with the predictors. Okay? Now let's go back a step. When we were discussing Poisson regression, I pointed out that if I did an analysis not of a normal Poisson variable, but of a yes, no, did you die in this time interval, but I fit it with the machinery of a Poisson regression and put in a dummy variable for each year, that was modeling the rate of death as a function of the predictors that I put into that regression. And so that was, in fact, a proportionate hazard model. And I call it pseudo-Poisson to emphasize that this isn't a Poisson regression. It just turns out that the likelihood for survival analysis, if you assume that the baseline hazard is constant within a year, is equal to that. And so I can use a Poisson regression program to estimate it. And so what we were modeling then is the hazard, the rate of dying in a small time interval. And we said that hazard depended on a bunch of predictors that we put in the model, But alas, it's true. No matter how many blueberries you eat, and even if smoking is zero and alcohol consumption is zero and everything else, people do die. And so there's a baseline hazard rate. And we didn't assume that baseline hazard rate was constant. We assumed it varied every year. That's what those dummy variables for each year represented. But within year, we assumed close enough, it's constant. And if we make that assumption, we can do our survival analysis using a Poisson regression program. In SAS, for example, ProcGenMod, in R, GLM. So, one question we should ask before we go on to doing other approaches to survival analysis is, how reasonable is it to make this assumption that the baseline hazard doesn't change that fast, that we need to worry about within year changes, that rather it changes slowly enough that a separate number for each year is a good approximation. Now remember, all these other risk factors are multiplying this baseline hazard, right? Because it's a proportionate hazard model, okay? But how do I determine whether this assumption here is reasonable? Well, here is a plot from CDC of the age-adjusted death rates for heart disease and cancer by sex in the United States from 1980 to 2001. So, is this the baseline hazard? The hazard if you had no other risk factors? Certainly not. Besides age, which is controlled for here, it's age-adjusted. Besides age and sex, there's smoking and various, there's body mass index, various other predictors. So having not controlled for these other predictors, which may be changing over time, this overestimates how much the baseline hazard rate changes. And let's look at it. So the hazard rate in men and in women for heart disease for men and women has been going down over time. And if you look at it, it's gone down, by a noticeable amount over time between 1980 and 2010, but that's a 30-year time interval. So if I ask, in each year, could I approximate that as constant? The answer is not too bad, but that may not be optimal. If I ask, in each year, could I approximate this with a linear time trend? The answer is yeah, that looks pretty good, right? It sort of looks like it's going down with a straight line. Cancer mortality rates have been changing much less over time. Clearly there, the baseline hazard could easily be approximated by a separate hazard for each year, and that'll do fine. And even for the cardiovascular disease, a lot of the drop in cardiovascular disease mortality over this time period comes from the fact that people started to quit smoking after the Surgeon General's report in the 60s. Takes about 20 years for that to start showing up in mortality rates. And so what we're seeing here would be a lot flatter if this also adjusted for smoking. And so I think it's reasonable to say that if we put in the usual suspects in our regression analysis to predict mortality rates, that a separate baseline rate for each year or a linear trend in the baseline rate in each year would probably do quite a good job. So that wouldn't be a bad thing to do, although you don't see that many papers doing it, and that's because I think people haven't realized that you can use Poisson regression to do a survival analysis. Okay? So, but there is a different pattern, as you saw, over time for men and women. So we're going to need a different baseline hazard for each of them. Okay? And that's important to remember. Now, everyone doesn't want to do that, and in some circumstances that may just be habit, and in other circumstances there may well be changes in the hazard in your cohort that aren't so well approximated by saying that there's a different baseline hazard every year. And so we want to talk about a more general way to approach that problem. And to do that, let's develop some vocabulary. Okay, so I'm going to let TI star be the time to failure, the age of death in the ith person. Why do I put a star there? Because this is a number that I may or may not observe. You have a grant from NIH to do a survival analysis in some cohort looking at some exposure. Everyone isn't dead in that cohort. You haven't observed the age at death for everyone. Okay? But what do we observe? Well, what we observe is how many people are left alive at any given time. So in 2006, I know how many people in my cohort were left alive. I may not know when they eventually died, but I know if they died by then or not. And so we can calculate the survivor function. And if I think about what that fraction is, it's the probability of surviving to time t, where t is 66, 75, whatever age you want it to be, or maybe you want it to be follow-up year 3 or follow-up year 5. There are different ways to define your failure time. And we'll talk about that later. But it's the probability of making it this far. And so that means that the survival function is the probability that your age of death is greater than t. And of course, your age of death is not necessarily the average age at death, right? So I've indexed that by I for the ith person. And here's an example of what a survivor curve looks like. It is, remember, the fraction of the population that's left at time t, or the probability of surviving to time t. It's a number between 0 and 1. It is not the number of people who are alive at time t. But you can easily get that by taking the number of people who started in your cohort and multiplying it by the fraction of them that were still alive at time t to get the number, right? But this is between 0 and 1, and it starts at 1. Everyone's alive when you recruit them, because if they're dead, they probably didn't answer your questionnaire very well, and then as time goes on, fewer and fewer of them are alive. Now, in this case, they're dying off pretty fast. Now, that might not be a reasonable survivor curve for the general population, but if you're studying cancer patients, for example, this may well be a reasonable curve. And that, again, is why I said, assuming that the baseline hazard is constant within a given year, may work well for the population as a whole, but not for some subgroups of interest. Okay? And so what we see here is this is 70% of the people left alive, and that occurs after 2 years. So 30% of these people died after 2 years of follow-up, right? And then half of them were dead by 4 years of follow-up. Okay, that's the survivor function. So how do I define the hazard? The hazard is the instantaneous rate of dying in a small time interval. So if I have a time interval going from tj to tj plus dt, a small increment of time, I can count how many people in my cohort died in that interval, right? And what's the denominator? Well, the denominator is the people who were at risk of dying in that time interval. So if you died before t sub j, whatever that time is, you're obviously no longer at risk. And so what I want to do is I want to calculate the rate of dying given that you survived up till time t sub j. Okay? And so surviving to t sub j is just the survivor function that we've just defined. So fortunately, we now know what that is. And that's going to be in the denominator for calculating this rate. And the numerator, as I said, is just the people who died in this time interval. But if it's a small time interval, then the number of deaths in that interval is just the probability of dying at time t sub j. Right? In the limit as dt goes to 0, the probability of dying in that time interval is just getting closer and closer to one number, t sub j. It's the probability of dying at that age. Okay? And so that's the probability. And if I multiply that probability by the number of people in my cohort, that's the number of people who died at that age, which, remember, may have a sort of funny looking distribution, the probability of dying at any given age. So I can define my hazard rate as the number of people who died at time t, or in a little interval around time t, which is the number of people in the cohort times the probability of dying at that time, divided by the population at risk, which is the number of people in the cohort times the survivor function. And so the number of people in the cohort cancels out, right? And it's just the probability of dying at time t divided by the survivor function at time t. So that's the definition of the hazard. And that's why it's the instantaneous rate of death, because I've sort of taken the limit as the interval t to t plus delta t got small. So that is our definition. That doesn't mean it's easy to compute. but that's the definition.